In this video, we're going to discuss the concept of dynamic chemical equilibrium. This is probably one of the more significant topics that we'll be covering all year long, as it plays a very large role in a lot of chemistry. Almost everything we've talked about so far in terms of chemical reactions can be recast in this light of equilibrium. We'll start with a quick rundown of the learning objectives in this video. The first thing in the first order of business will be determining what a chemical equilibrium actually is, and we'll have a couple steps leading into that process. And once we identify what the actual chemical equilibrium is, we'll then talk about some of the actual details of what chemical equilibria are all about. We'll talk about something primarily known as the equilibrium constant. This was originally referred to as the law of mass action by the scientists who originally came up with the concept, later referred to as the law of chemical equilibria, all of which leads into something we'll be working with a lot, known as the equilibrium expression. Before we dive into the actual discussion itself, a quick example of this process and why equilibria is so important. We've talked a couple times over the year about this Haber process, the chemical formation of ammonia from gaseous nitrogen and gaseous hydrogen, a significant process in terms of generating fertilizers that has fueled the agricultural growth here in our country. Over here we can see a diagram of how the system works. We pump in nitrogen gas and hydrogen gas. They are compressed in a compressor and reacted into a reaction vessel here. The chemicals react together, create ammonia. The ammonia is removed from the process, but unfortunately at the time, the forward reaction creates ammonia, but there's also a reverse reaction that occurs that goes back and breaks down that ammonia to create nitrogen and hydrogen gas. As a result, there's always leftover hydrogen and nitrogen, which then gets recycled back into the process to be used as reactants again in order to create more product. This removal of the ammonia and the recycling of the hydrogen and nitrogen are all ideas that were put into place based on our scientists' understanding of how equilibria work. And between this video and the video you'll watch next about Le Chatelier's principle, we'll have an explanation for why this works the way it does. As I said, the beginning of our discussion is to determine what a chemical equilibrium actually is. To do this, we're going to look at a couple different chemical reactions and how they are different. So to start, we'll talk about things in terms of forward reactions and reverse reactions. This reaction is the combustion of hydrogen gas with oxygen, unfortunately not balanced. But what we point out from this thing is once you get this reaction going, it happens on its own. Hydrogen is well known for burning very easily. We would describe this process in terms of thermodynamics as being a spontaneous process, a reaction that can happen given its own energy. We can then take this reaction and run it in reverse. We can take the water and separate it back into hydrogen and oxygen. This is a process known as electrolysis. You have to induce an electrical current to your water and it'll pull it apart. But unlike the forward reaction, this reverse reaction is non-spontaneous. Water doesn't generally do this on its own. As a result, we think of this reaction as being a one-direction reaction. Once you form the H2O in the original forward process, it is permanent. It doesn't go away unless you force the reverse reaction. And in this case, that would require, again, a strong electrical charge. We have thought so far this year about all chemical reactions in this way as happening only naturally in the forward direction. Let's take a look at a second example here involving some new chemical reactions. Again, we have our forward reaction, and we're going back to our Haber process reaction here. Nitrogen plus hydrogen gas reacts to make ammonia, and we would describe, again, this process as being relatively spontaneous. When you put these two chemicals together under the right conditions, they react. We could take a look again at the reverse reaction, in which case the ammonia decomposes to form the nitrogen gas and the hydrogen gas separately. And the thing that makes this process different is that this reverse reaction is also spontaneous, again under the right sets of conditions. So because the forward reaction can happen by itself and the reverse reaction can happen by itself, as soon as that ammonia is formed in the forward reaction, it immediately starts to decompose to form nitrogen and hydrogen. The nitrogen and hydrogen then start to react again to form ammonia, and we can go around this circle over and over and over again. So when you run this reaction, neither of these is the only reaction that happens. You necessarily end up getting both the forward and the reverse reaction happening at the same time. And this what brings us to an actual idea of what an equilibrium is all about. To show that both reactions happen at the same time and that there's a constant forwards and backwards reaction occurring, we use a different arrow to show the process here. We can draw both of those reactions on the same time by using this guy here, which we refer to as the double arrow. Part of it's showing that the reaction is going forwards, and then another part is showing that the reaction is happening in reverse. That brings us to our official definition of what a dynamic chemical equilibrium is. It's basically any chemical process that simultaneously produces product in a forward reaction and reactant in a reverse reaction. And as a result, both reactions are always happening in this process. As soon as product is created, it breaks down to make reactants. As soon as reactants are present, they form products, and both of them are always happening. But the equilibrium term, the word equilibrium implies that there's some sort of balance going on here, and that balance occurs in the fact that the amount of products formed or the amount of reactants left over always stay the same. So we're always making product, and product's always getting used to make reactants, and then vice versa, but the reaction amounts stay consistent, and that's the balance we're talking about when we say equilibrium. Let's see if we can explain this process in a little bit more detail here. We've got our ammonia or our nitrogen reacting with our hydrogen, and as the forward reaction occurs, nitrogen and hydrogen gas are used up, and because there's less of it around, the forward reaction begins to slow down, and it happens less and less and less. As the ammonia is formed, the reverse reaction starts to speed up. There are more ammonia molecules around, and there are more likely opportunities for those ammonia molecules to break down. Eventually, that forward reaction slows, that reverse reaction starts to speed up again. You eventually reach something we'll refer to as like a balance point. The forward reaction is slowed enough, the reverse reaction is speeded up, so that ultimately the reaction rates for forward and reverse eventually end up being equal to one another, and that's when we've reached what we would call equilibrium. We can represent this graphically using the graphs here on the left. We have red representing our forward reaction rate and blue representing our reverse reaction rate. We can see that over time, if this line right here represents the start of our reaction, over time our reaction rate slows down and gets slower and slower, and this is happening because our reactants are using up. Fewer reactants means fewer reactions can occur. At the same time as the product's being formed, the reverse reaction starts to speed up again, and we get more and more of that reverse reaction. And eventually, both of these guys end up meeting the middle. When those forward and reverse rates are equal to one another, that's when we've reached what we would call equilibrium. We can also see this not in terms of just rates, but also amounts of product and reactant formed. As the reaction proceeds forwards, the amount of reactants we have increases, but notice as we go further and further time, because of the slower rate, the end result is the amount of reactants starts to become level. Likewise, as products form, they form slower and slower and slower as we have less and less reactants to work with, and the end result is, again, we reach equilibrium. Now, it's important to note that the equilibrium rates are the same, but the equilibrium amounts can necessarily be different. And how to figure out these equilibrium amounts is what we'll talk about later on in terms of something called an equilibrium constant. So here we are then, discussion about the equilibrium constant. This is basically a way of quantifying the rates that we were talking about before and this idea of equilibrium. As we talked about, the equilibrium is a balance point, is unique for each individual reactions. Some chemical reactions favor making more product. Some chemical reactions favor making more reactant, but there's always some sort of balance that is struck there. This balance point is something that ultimately can be measured, and we measure that in the form of the equilibrium constant itself. And what this is really just a ratio of the amount of product to reactant present when the reaction is at equilibrium. So for example, reactions that favor product are going to have a higher ratio, reactants that favor reactant are going to have a lower ratio. And we can quantify that. The symbol we use for the equilibrium constant is K for constant and EQ for its equilibrium. There's actually a lot of different values of K out there, and we'll talk about a couple more before the year's done. And as we already mentioned, if KEQ is greater than 1, that means our ratio has more product in it than reactant, and the end result is we would say that this reaction favors product. And if our KEQ value is less than 1, then that means our reaction favors the reactant part of the reaction, and as a result will produce a little less product. And we would say that this guy favors a KEQ less than 1 is a reaction that favors the reactant. Typically as chemists, we tend to like this one better because we're generally trying to produce products for a reaction, but realistically speaking, you got to wrestle with both. These are two scientists by the name of Cato Goldberg and another scientist by the name of Peter Varga. You pronounce the names a little strangely simply because, again, these are Norwegian scientists. Anyway, two Norwegian chemists, both born in the 1930s. I think one was 1933 and the other 1936. And they actually happened to be brothers-in-law. That's how they got together to do their actual work. The main discovery both are credited with is the concept of the law of mass action, which is eventually developed into the law of chemical equilibrium. The idea that these dynamic equilibrium exist and that we can mathematically represent them with both an equilibrium constant, which we've already talked about, and an equilibrium expression, which we're going to be dealing with in a few minutes. The work that they came up with, this equilibrium idea, was definitely underappreciated at the time. This is because scientists really didn't know what to do with this at this stage in the game. It wasn't really applicable yet. However, despite being underappreciated, they're certainly appreciated now, both of them were considered to be very successful chemists, and they were very highly regarded by their peers for the work that they were putting forth into the world. So let's get into the actual results of what Goldberg and Varga actually came up with. What I have up here is kind of just a dummy chemical reaction, and this is the format we typically use for these types of things. The little a represents the coefficients from the balanced chemical reaction. The big A represents the actual chemical itself. So there's A number of chemical A, there's B number of chemical B, and they react to make chemicals C and D respectively. The equilibrium expression, which is what this equation is right here, is probably the most important part of what we're doing here. And this is basically how we get this value of K, or our equilibrium constant. It's basically equal to the concentration of the two products, and by the way, these brackets denote concentration, specifically in molarity. But anyway, it's basically the concentration of the two product chemicals, chemicals C and D, divided by the concentration of the two reactant chemicals, which would be chemicals A and B. And that's what we have over here. It's the idea of products divided by reactants as our ratio. A chemical that forms more products than the reactants is going to get a larger value for K than one that forms more reactants than products at equilibrium. Now you'll also notice these little guys up here, the coefficients of the balanced chemical equation also affect this value for KEQ. You take that concentration of chemical C and you bring it to the power of whatever its coefficient is in the balanced chemical reaction. So C to the C power, D to the D power, etc., etc. And remember, when these places are left blank, that means 1. Last piece of the puzzle then before we try one of these is this value of K then, the expression is easy to set up, is measured experimentally, and it is unique for each individual substance. It's unique for each chemical reaction, and it's also unique for specific reaction conditions, i.e. different temperatures and different pressures will result in different values of K. And again, that's something we'll talk more about in the next video when we're discussing something called Le Chatelier's principle. So here again we have our Haber process chemical reaction. What I'd like to do in this scenario is simply create an equilibrium expression based on the reaction that we have. So our value in this case of KEQ is always going to be equal to the concentration of all the products divided by the concentration of all the reactants. In this case our product is just NH3, so we're going to do bracket to denote concentration. We're going to put in the chemical formula for our product, and because the balanced chemical reaction tells us there are two of them, we're going to have to square that value. So it's going to be the concentration of the ammonia squared divided by the concentration of the nitrogen taken to the first power because its coefficient is 1 times the concentration of the hydrogen gas taken to the third power because its coefficient is 3. In an actual problem, you'd be probably given the value for KEQ. You'd be told, for example, how much nitrogen and hydrogen you put in. You would allow the reaction to run until it reached equilibrium, and then you might be asked, what's the concentration of ammonia as a result of all of this? So just like any other algebraic expression, you'll be given a bunch of variables and asked for solve for something that's missing. So that's pretty much it in terms of our discussion here. A quick list of things you should be able to do at this point. You should be able to describe what a forward and reverse reaction is. You should be able to talk about the role of reaction spontaneity in equilibrium. It determines whether you'll have an equilibrium or you'll just have a forward reaction. You should be able to define the term equilibrium itself and also be able to talk about the dynamic part, the fact that we don't change quantities of chemicals, but the reactions are constantly running, churning out more product, which then gets churned out to make more reactants. You should be able to briefly describe what the equilibrium constant is, and probably most important out of all these things, you should be able to work with the equilibrium expression. And I expect you guys to be able to write an equilibrium expression based off of a balanced chemical reaction. Not a very difficult thing to do, but definitely a fundamental skill when working with equilibrium reactions of any type.